Something extraordinary happened in our solar system, and it wasn't supposed to be seen, not by any plan, not by any prediction, but by sheer coincidence captured entirely by NASA's Hubble Space Telescope. Imagine a telescope that spends decades observing distant stars, galaxies, and comets, suddenly catching a cosmic event so rare that it challenges everything scientists thought they knew. That event revolves around a comet called C 2025 K1, or K1 for short. What makes K1 remarkable isn't just that it passed through our solar system. It's that it didn't survive intact. It didn't just brush the Sunday. It shattered, and the Hubble caught every detail in real time. The story begins on November 8, 2025. Hubble was scheduled to observe a completely different comet, part of an organized program that scientists had spent months planning. Then, something unexpected happened. The original target became unobservable due to what the team described as technical constraints. The precise meaning is unclear, but the result was a sudden scramble. Researchers had minutes, maybe hours, to select a replacement target. They chose K1, a comet discovered by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a network designed to find objects that could come close to Earth. For most telescopes, catching a comet at the moment it begins to break apart is nearly impossible. Comets typically fragment far from human instruments, and by the time observations are possible, the pieces have already drifted apart. But Hubble was pointed at K1 at exactly the right time. In the first 2.0-second exposure on November 8th, something immediately stood out. There weren't one but four distinct comet-like objects in the frame. Each fragment carried its own coma, the glowing envelope of gas and dust surrounding a nucleus. By the second day, the largest fragment had split again, creating three moving pieces along an invisible line. By the third day, the fragments had spread further along a diagonal path across the field of view. K1 wasn't just traveling through space, it was dying. It was tearing itself apart, and Hubble was the only instrument sharp enough to capture the process as it happened. This is what astronomers mean by a slim chance. In its 5-year history, Hubble had never observed a comet fragmenting this early, this close to the onset of its breakup. Never before has Hubble caught a fragmenting comet this close to when it actually fell apart, said researcher John Noonan. What makes K1 even more baffling is its timeline. The fragmentation began roughly 8 days before Hubble observed it, placing the start of the breakup around October 31st, Halloween 2025. A comet roughly 5 miles across the size of a small town had survived its closest approach to the Sun, its perihelion, and then slowly began to collapse. K1's perihelion had brought it inside Mercury's orbit, where temperatures exceeded 800 degrees Fahrenheit and gravitational forces shredded almost anything that ventured that close. The comet survived the Sun's furnace, only to break apart quietly days later, as if the heat had planted the seeds of its destruction. And when it finally cracked, physics predicted an immediate surge in brightness. The freshly exposed ice inside a comet should sublimate almost instantly, creating dramatic tails of gas and dust, but K1 refused to behave. Ground-based telescopes saw a delay, a silence. The expected brightening didn't happen. The comet cracked, but the outburst was suppressed, defying every model scientists had used for decades. This isn't just a quirky footnote in astronomy. K1 was acting like something fundamentally different from every comet previously studied. It had layers, an outer, processed shell, and an interior of primordial ice, untouched for billions of years. And as Hubble observed the breakup, instruments detected something truly anomalous. K1 was carbon depleted, a chemical signature unlike anything seen in other comets, where carbon is typically abundant. The discovery raised more questions than it answered, and Hubble's timely observation might have been the only chance to capture it. The comet is now drifting 250 million miles away, never likely to return. What Hubble recorded in those brief exposures may be the only glimpse humanity will ever have of this unique object. If you like, I can immediately continue with part 2, picking up seamlessly from this point, diving deeper into the fragmentation process, K1's anomalous chemistry, and its implications for solar system science. The more scientists dug into K1's behavior, the stranger it became. Comets are supposed to follow predictable rules. Ice sublimates, dust streams outward, and fragments drift apart in a way that models can anticipate. But K1 broke those rules. The fragmentation wasn't a single explosive event. Hubble revealed a sequential breakup, as if the comet were collapsing from the inside out in stages. First, the main nucleus split. Then, a smaller fragment cracked again, and the remaining pieces continued along a precise trajectory, almost like a domino effect. Researchers were able to reconstruct the timeline, tracing each fragment's path backward to a single origin point. The comet had begun breaking apart 8 days earlier, but the universe's timing and Hubble's schedule allowed humans to witness it like never before. Even more puzzling was the comet's chemistry. Every comet studied closely before had abundant carbon, the building block of organic molecules, and a key ingredient in understanding the early solar system. But K1 was severely carbon depleted. The readings were so unexpected that researchers double-checked and triple-checked the instruments before accepting the result. There was no known model in astrophysics that explained such a chemical profile. The comet's outer layers appeared processed and ancient, while its interior, which had remained frozen for billions of years, didn't match anything previously observed. It was as if K1 were a relic from a corner of the solar system we've never explored, holding secrets no telescope has seen until now. Scientists have offered a few explanations, each plausible yet unsatisfying. One theory is that a thin, desiccated dust layer could have formed over the exposed ice, temporarily suppressing sublimation after the fragmentation. Another suggests that heat from the sun had to accumulate inside the nucleus before building enough pressure to eject material outward. Both mechanisms make sense, but they only deepen the mystery. If K1's interior is preserved in this way, it means the comet is layered and complex, not a simple ball of frozen material. Each fragment contains a chemical time capsule from the solar system's formation, untouched by the sun for billions of years. The timing and uniqueness of Hubble's observations are almost miraculous. Ground-based telescopes worldwide monitored K1 after the fragmentation, but none could capture the early stages in such fine detail. By the time the data reached the public, K1 was already 250 million miles away, drifting outward on a path that makes it unlikely ever to return. Every hour, the fragments spread farther, the ice sublimates, and the chance to study these materials up close diminishes. The window for observation closed almost as quickly as it opened, leaving scientists with only what Hubble captured in those critical frames and the early spectrographic readings. Adding another layer of intrigue is the comet's connection to the Atlas survey network. Atlas had previously detected 3I, Atlas, an interstellar object that entered our solar system from outside, sparking global attention and months of debate over its origin and unusual properties. K1, a solar system comet, also flagged by Atlas, behaves in ways that defy conventional physics. While K1 and 3I, Atlas are different objects, they share the same detection system, the same temporal window, and a similarity that no one in the scientific literature has publicly addressed. Two anomalous discoveries, same year, same network. It's a coincidence, or it could be a hint at something far more complex in our solar system's outer reaches. K1's perihelion adds to the story. The comet survived passage inside Mercury's orbit, enduring temperatures above 800 degrees Fahrenheit and intense tidal forces. Yet, the breakup didn't occur immediately. Instead, it delayed by 8 days, suggesting a slow collapse caused by the difference between the sunlit and shadowed side of the nucleus. The sequential fragmentation observed by Hubble shows that the comet's structural integrity held just long enough to delay the inevitable, making the event one of the rarest observed in modern astronomy. This brings us back to the chemical anomaly. Carbon depletion in K1 challenges everything we thought we knew about solar system formation. The comet carries material that doesn't match any known source. The spectrographs aboard Hubble-STATI and CAS detect ultraviolet signatures that ground-based telescopes cannot. The full chemical portrait hasn't been released yet, but preliminary results hint at something that could rewrite aspects of planetary science, a glimpse into primordial material that has never been studied before. And yet, the comet is gone. Its fragments are scattering across 250 million miles of space, leaving behind only the faint traces captured in Hubble's images and the incomplete chemical data. The questions K1 raises may remain unanswered for decades. How did a comet survive perihelion only to collapse days later? Why is it carbon depleted? Could there be other bodies like K1 hiding at the edges of our solar system, carrying secrets older than the planets themselves? The story of K1 is just beginning, and the answers may not be simple. Scientists are still analyzing the spectrographic data, and the implications of what Hubble captured could force a rethink of solar system evolution. But one thing is certain: the universe doesn't always play by the rules we expect, and sometimes the rarest observations happen purely by accident. As we follow K1 outward into the void, the scale of what Hubble captured becomes staggering. Think about it. A 5-mile-wide comet, larger than many long-period comets, drifting through the solar system for millions of years, and we were lucky enough to catch the exact moment it began to fragment. For context, this isn't something that happens often. Comet breakups are usually spotted weeks, even months, after the fact, long after the initial fragmentation. Hubble's timing was unprecedented. The instrument wasn't just lucky, it was virtually the only tool capable of observing the event with this level of precision. Every frame, every fragment, every stream of gas and dust captured a process that had unfolded for billions of years in silence, only now revealed to human eyes. The fragmentation itself is as precise as it is unusual. K1 didn't explode in a chaotic burst. Instead, it failed in a controlled sequence, as if the comet's internal structure dictated the order. First, the main nucleus cracked. Then one of the smaller fragments split further, and the remaining pieces followed a diagonal path, almost like clockwork. Scientists could trace each fragment's trajectory back to October 31st, 2025, 8 days before the first Hubble frame, Halloween. While the date is coincidental, the timeline reveals something remarkable. The comet survived the harshest part of its journey, perihelion, intact, only to fracture days later. That delay is itself a mystery. Physically, the delay makes sense in broad strokes. A comet that survives intense solar heating may crack internally, but the layers can hold, preventing immediate disintegration. Then, temperature differences between the sunlit side and the shadow side stress the nucleus further, finally overcoming its internal cohesion. But K1's behavior isn't fully explained by physics as we currently understand it. When a comet fragments, the exposed interior, ancient ice, and frozen organic compounds should sublimate instantly, creating a dramatic brightening visible to ground-based telescopes. K1 didn't do that. There was anomalous silence. Hours, even days, passed before the expected outgassing began. Something delayed the reaction. Researchers theorized that a thin, desiccated dust layer could form over the newly exposed ice, suppressing sublimation temporarily. Alternatively, subsurface heat might have needed time to accumulate, building enough pressure to eject material outward. Both mechanisms are physically plausible, yet they highlight an uncomfortable truth. K1's interior isn't uniform. The comet is layered and complex. with a processed outer crust and an inner core that hasn't seen sunlight in hundreds of millions, possibly billions, of years. It's a frozen time capsule, carrying materials from the era before planets even existed, now scattered across millions of miles of space. And the chemical anomalies make the story even more compelling. Every comet we've studied closely, Halley, Tempel 1, Churyumov-Gerasimenko, contains abundant carbon, a critical ingredient in understanding early solar system chemistry. K1, significantly depleted. The readings are so unexpected that spectroscopists had to verify their instruments multiple times. Carbon is the backbone of organic chemistry. Its absence, or near absence, in a comet nucleus challenges everything we thought we knew about comet formation and composition. The ultraviolet spectrographs aboard Hubble STE and CAS are now processing the full dataset, but the results could take months to release. Consider the implications. Comets are our windows into the early solar system. They preserve material from the time of planetary formation, offering insight into the chemistry that predated Earth, oceans, and life itself. K1's interior doesn't fit the established patterns. Its carbon depletion, delayed fragmentation, and sequential breakup suggest a structure unlike any comet we've observed. By the time the public heard about it, the comet was already 250 million miles away, drifting outward on a trajectory that makes it unlikely to ever return. The opportunity to study it in detail, close up, has effectively vanished. The story of K1 also intersects with the Atlas survey system, the same network that discovered 3I, Atlas, an interstellar object with characteristics that left scientists puzzled for months. While K1 is a solar system comet and 3I, Atlas, is an interstellar visitor, both were discovered in the same year by the same network, both produce anomalies that defy easy explanation, and both challenge our understanding of small bodies in the solar system. Whether that's coincidence or the hint of a larger pattern we haven't yet recognized remains an open question. Finally, the sequential nature of K1's breakup tells a story about internal composition and structural integrity. The comet didn't simply explode, it failed gradually, exposing layers of ancient material at different times. Every fragment, every split, carries a piece of history older than the Earth itself. And as those fragments continue outward, the clock on our opportunity to study them ticks away, leaving us with only the frames Hubble captured and the partial spectroscopic analysis still being processed. What K1 reveals isn't just the story of a single comet, it's a window into the deep outer reaches of our solar system, regions we've never observed directly. Most of what we know about this part of space comes from inference, occasional long-period comets that drift inward, or distant bodies barely visible as faint points of light. K1, however, gave us something unprecedented, high-resolution data on material that has been untouched for billions of years. Its interior is effectively a frozen archive, carrying chemical signatures from the solar system's formation. And yet, even in this pristine material, we see something completely unexpected, a dramatic depletion of carbon, one of the fundamental building blocks of organic chemistry. Every comet we've studied up close, Halley, Tempel 1, 67P, Churyumov-Gerasimenko, has shown abundant carbon compounds. They're present in the ice, the dust, and the organic molecules released as the comet heats near the sun. Carbon is ubiquitous. It's essential for understanding the chemical pathways that could lead to life. With K1, the instruments measured significantly less carbon than expected, enough for scientists to pause, recheck their calibrations, and triple-check the readings. In spectroscopic terms, this is not a minor anomaly, it's a fundamental outlier. K1 does not fit the patterns we've seen in the solar system's building blocks. Its chemistry challenges the assumption that all comets from the outer solar system share a similar primordial composition. And then there's the fragmentation timeline. Most comets that break apart do so either at perihelion closest approach to the Sun or shortly thereafter. Physics predicts that exposure to extreme heat and gravitational stress causes near instantaneous fragmentation. K1 defied this expectation. It passed inside Mercury's orbit with surface temperatures exceeding 800 degrees Fahrenheit and survived. Only 8 days later did it begin to break apart. Even more puzzling, the fragments didn't erupt in a sudden blaze of sublimation. Instead, the comet stayed eerily calm, almost as if the ice resisted immediate outgassing. Scientists proposed explanations, each plausible, but raising more questions. Perhaps a thin layer of desiccated dust formed over the exposed ice, delaying sublimation. Or maybe internal heat needed time to build up enough pressure to eject material outward. Both mechanisms could account for the delayed breakup, but they also imply a highly differentiated internal structure. An outer crust hardened by eons of solar radiation and space weathering, and an inner core preserved almost untouched since the solar system formed. The comet is not a simple frozen ball, it's a layered, complex archive of cosmic history, now dispersing into the solar system as fragments and gas. Then there's the broader context. K1 is part of the Atlas Discovery Network, the same system that identified 3I, Atlas, an interstellar object that baffled scientists in 2025. While K1 is a solar system body and 3I, Atlas came from beyond, both share anomalous behaviors, unusual trajectories, unexpected chemical compositions, and characteristics that don't match traditional models. Two unprecedented events detected by the same survey system in the same year. Coincidence? Maybe. But the correlation is striking and raises questions about what other surprises may be hiding in the outer reaches of our solar system. The Hubble observations also highlight the limits of our current observational window. By the time the public learned about K1 in March 2026, the comet was already 250 million miles away, drifting outward, fragments spreading, ice sublimating, and signals weakening. The opportunity to study it with the precision of Hubble or any high-resolution instrument had already passed. What remains is a finite set of frames and spectroscopic data, some of it still being processed, particularly in the ultraviolet range. These readings could hold answers to questions we haven't yet framed about K1's composition, its origin, and the processes that shaped it. In short, K1 challenges assumptions at every level. Its delayed fragmentation, sequential breakup, layered internal structure, and carbon depletion all suggest that our understanding of long-period comets is incomplete. It's a body that has survived the solar system for billions of years, preserved material from its formation, and now is dissolving into the void, leaving only a snapshot of its final days for scientists to study. The comet is gone, but the questions it raises about the early solar system, cometary chemistry, and the processes that shaped these ancient bodies will remain with researchers for decades. If you want, I can continue immediately with Part 5, where we'll explore what K1's anomalous carbon depletion might mean for our understanding of organic chemistry in the early solar system, and why this could reshape fundamental planetary science. K1's carbon depletion isn't just a small anomaly, it's a signal that something about its formation or history was radically different from every other comet we've studied. Carbon is the backbone of organic chemistry, and comets are considered some of the most reliable repositories of primordial solar system material. When a comet, like K1, shows a significant deficit, it challenges assumptions about how and where these bodies formed. Did K1 originate in a part of the solar system that was chemically distinct? Did it somehow lose its carbon over billions of years? Or is there a process at work that we've never observed before, silently reshaping its composition long before it ever approached the Sun? These are not easy questions to answer, and the current data leaves room for multiple interpretations, each carrying profound implications. Even the sequential breakup of K1 raises puzzles. Most fragmented comets shatter chaotically, breaking apart in a random, often explosive pattern. K1, however, disintegrated in a precise order, almost like a structure failing from the inside out. First, the main nucleus cracked, then a secondary fragment split, and the final pieces continued along predictable trajectories. Hubble's incredible resolution allowed researchers to trace these fragments backward to the exact point and time of their origin, reconstructing the comet's collapse in unprecedented detail. This is the first time a long-period comet has been observed fragmenting so close to its initial breakup, a timeline that is normally lost in the weeks or months before ground-based telescopes can catch it. The more scientists look at K1, the more it highlights a gap in our understanding of comet physics. The outer layer must have been resilient enough to survive extreme solar heating, while the interior contained untouched material, including ice and organics frozen since the birth of the solar system. That material, now slowly dispersing across hundreds of millions of miles, is a chemical time capsule. It carries the history of the solar system's earliest years, including processes that may have contributed to the formation of planets and potentially even the preconditions for life. Yet, because K1's fragments are drifting outward and fading, we may never get a second chance to study them with the same precision. The window is closing, and the clock is ticking. Then there's the comparison to 3I Atlas, the interstellar object discovered by the same survey network in the same year. While K1 is confirmed as a solar system comet, its anomalous behavior delayed fragmentation. Unusual chemistry mirrors the strangeness of 3I Atlas. Two objects, same discovery system, same year, both defying expectations. Even if there's no direct connection, the pattern is striking. It raises a broader question. Are there unknown processes operating in the outer solar system that produce objects unlike anything we've cataloged before? If so, K1 might not be an exception, but a glimpse into a category of bodies that we've never observed directly. What makes this all the more urgent is the ephemeral nature of K1 itself. Hubble captured those images in early November 2025, and the peer-reviewed paper documenting the event wasn't published until March 2026. In that time, the comet traveled hundreds of millions of miles away, fragments spreading and fading into the vastness of space. Instruments that could study it at close range are now useless for detailed analysis. All we have are the 320 frames from Hubble and the spectroscopic readings taken immediately after the breakup. Even now, some of that data, particularly in ultraviolet wavelengths, is still being processed. Scientists are holding back conclusions until every possible measurement can be verified. K1 is gone, but its story isn't. The comet represents a rare chance to peer into the solar system's distant past, exposing materials untouched for billions of years, and in doing so, revealing behaviors and compositions that challenge long-held models. Its delayed fragmentation, sequential breakup, and carbon anomaly all signal that there's more to learn about the formation of comets, the chemical evolution of the solar system, and perhaps even the conditions that gave rise to life on Earth. In the next part, we'll explore the broader implications of K1's anomalies, what this comet can tell us about solar system formation, planetary chemistry, and why researchers are keeping some of the most intriguing details tightly under wraps. By the end, you'll understand why K1 isn't just another comet, it's a cosmic mystery that could rewrite textbooks.